So to measure the distance among observations described using numerical attributes, we will use Minkowski distance. Minkowski distance is a very popular distance measure on numerical data. Here we have this formula. So you see probably right away that it's very similar to Euclidean distance. If we put 2 here, replace h. So to describe what this formula says, I here represents our observation 1 and j is observation 2, that we compare the distance between these two observations. And those two observations are measured on p attributes. A set of p attributes describe objects, observation I and observation j. H is the order, and h can be set to different values to obtain different measures. So if h is 2, we have Euclidean distance. If h is 1, we have Manhattan distance. We're going to look at those. The distance is so defined, it is also called a L-H norm. You're going to see L1 norm, L2 norm very frequently in machine learning literature, in neural network methods. So this is the Minkowski distance. Minkowski distance has the 3 properties that make it a metric. In the slides in the note section, I discussed why a distance being a metric is useful. So it's not really related to this course, but having those distance, having those properties make not only intuitive sense, but also mathematical sense, have general applications. So those properties are distance can never be negative. If the two things are not the same, then that distance must be greater than 0. If they're the same, the distance has to be 0, right? So this is why when we talk about the distance, we know that the lower bound is 0, but we don't know what upper bound might be. The upper bound might be greater than 1. And also, Minkowski distance has the symmetric is symmetrical. So the distance between I and j is the same as the distance between j and I. Okay. Not all distance measures used in machine learning actually have this property, but Minkowski does. Triangular inequality. So if you imagine ijk, 3 dots here, anything, the distance between those two is always going to be greater than the direct distance between these two. Okay, so I'm drawing an invisible triangle here. So that's triangle inequality. Okay. So special cases of Minkowski distance, when h is 1, it's Manhattan distance, city block. So that the previous formula are going to be become this when we replaced h to 1. When h is 2, which is L2 norm, it's Euclidean distance. When h is approaching positive infinity, we have supremum distance, which is basically the maximum difference between any component attribute of the two observations. When h approaching to negative infinity, the distance actually measures is directly the minimum difference between any attributes of the two observations. We're going to see example of that next. So we have those points. We have a vector space. Here we have those points that we plotted here. X1 is 1 and 2, so it's right here. And we also plotted 2, 3, and 4. So the Manhattan distance between, let's say, just use 1, 2 an example. Manhattan, remember, it's city block, so we cannot go cut through buildings. We have to make rectangular turns. So here we have this edge gave us 2, this edge gave us 3. Therefore, the Manhattan distance between x1 and x2 is 5, which is documented here. So city block, okay, you have to go through that. You do that, it's the same thing. Euclidean distance is basically the distance between 2 points measured through a straight line. So Euclidean distance using the formula that provided earlier, which is the square root of the 2 squared and the sum of the 2 squared and the 3 squared, which gave us this value, 3.61. That's Euclidean distance, which is basically the length of this line between x1 and x2. The supremum, remember, that was the maximum value of any of those attributes. So here the distance for this attribute, the distance is 2. For this attribute, the distance is 3. So therefore, the supremum distance between x1 and x2 would be 3, which is documented here. Okay. So when we talk about numerical attributes, there is a special phenomenon that we need to pay attention is numerical values can be measured on different scales. When you measure things on different scales, then it's hard to make a comparison. So for example, a SAT score and students' ACT score can be very different. How can we compare a SAT score of 1800 to an ACT score of 24? A commonly used way to perform this comparison is to standardize the value. It's also called normalization. So if we know in the population of the student taking SAT, we know the mean score. If we know the standard deviation, if we know the same for ACT test, we will be able to normalize those scores. This normalization is called Z-score normalization. Z-score normalization basically gives you a score that tells you how this observation, 1800, is how many standard deviation away from its mean. So here we have the standard deviation, 300. The mean score of all students taking the test is 1800. Then we can actually standardize students' A score to this number. Actually, it's 1. And we can do the same for student B's ACT score. We use the student's ACT score minus its mean, 21, and divided by its standard deviation. Again, this score of 0.6 is how many standard deviation away 24 is from 21. So 24 is 0.6 standard deviation away from 21. So this actually gives you a way, after those two scores are normalized, we can actually directly compare 1 to 0.6. We know student A performed better compared to all the students taking the score. Okay, it's used very widely. So this is the Z-score, and we already look at example and we know how to compute it. Z-score can have negative values when X is below the mean. Earlier, remember standard deviation? when we discussed standard deviation, we talked about an alternative way to measure data dispersion. That was the mean absolute deviation, where we don't use the square, but we take the absolute value between a value to its mean. So M is sample mean here. We can use z-score instead of using standard deviation. We can replace this with the mean absolute deviation. It gives you similar result, but when you have extreme outliers, using mean absolute deviation would be a more robust measure. We talked about this before, so we're repeating something that we already learned. So the next topic we're going to cover is how we covered binary, nominal, and numerical data. What about ordinal variables? How do we measure the similarity between ordinal variables? The idea here is to convert. Okay, let's first review what was the ordinal variables. Ordinal variables are the variables that take values, and those values are in an order. For example, we could have grades of students in a math class, and those grades are A, B, C, D, E. So for math grade, math score, student A, student 2, student 1, 2, 3 have different scores, and those scores are ordered. A is better than B, B is better than E, right? So when we have this data, we can actually convert them into numerical data by doing the following. First, we will replace this value by its rank. So A is 1 and E is 5. So A is being replaced with 1, B is 2, and E is 5. Okay. And then we can map the range of each variable to 0 and 1. How are we going to do that? We can do that by simply do a simple division. So for example, student A, we have rank 1. We will use his rank minus 1 divided by total possible ranks. There is 5. A, B, C, D, E. We have 5 ranks, right? Divided by 5 minus 1. So this will give us a score of 0. And the student B going to have a score, do the same thing. So in this case, we'll have 2 minus 1 divided by 5 minus 1. We're going to have a value of 0.5. And lastly, this 5, we're going to have 5 minus 1 divided by 5 minus 1. That gives us 1. So we basically converted A, B, E to the range, to the value that falls in the range of 0 and 1. If you feel it's awkward that you want student A to have 1 and student E to have 0, you basically only need to change your ranking scale. You put 5 up here and you put 1 up down there, okay? So once we convert those things into numerical value, then we can start to use Euclidean distance to compute the similarity, okay? So we have covered all 4 types. Ratio data are going to be treated as the same as numerical as data. So using Euclidean distance, Manhattan distance, Minkowski distance, basically in general, can help us to compute a proximity between 2 observations. So now we come back to the question that when we have real data set, we're bound to have attribute types that are mixed. We could very likely use both nominal, symmetrical binary, asymmetrical binary, numerical, and ordinal data in our data set, describing our observations. When that's the case, then we can use a weighted formula. Remember weighted sum? This is where we're going to use weighted mean. Where did we talk about that? Right here. So weighted arithmetic mean. So we're going to use that idea here when we compute proximity between of mixed type attributes. So here, this formula looks very, very complex, but it's exactly the same as the weighted arithmetic mean formula. If we want to compute the distance between objects I and objects J over F different attributes, and those attributes can be nominal, binary, numerical, or ordinal. Here, this delta is weight, and this is the distance for certain attributes. And we're going to get a weighted sum over all attributes and divide it by the sum of all weights. Okay, so this is exactly the same formula as we have before. And now, how do we compute distance between two observations over one attribute? We just learned that. For every type of attributes, we learned how to compute. If this attribute or feature is binary or nominal, if the value are the same, the distance is going to be 0 because they're the same. There's no distance between them. If the values are not the same, then the distance is 1. Okay. If f is numerical, then we will normalize this attribute using z-score normalization, and then just compute the distance between the two, simple arithmetic distance. If f is ordinal data, again, we just talked about it. We convert ordinal data to numerical data, and then use numerical data method to deal with it. Okay, so this is how we compute the distance on a specific feature. And now how do we decide weight? Weight only take two values. It's either 0 or 1. When it's 0, basically it says disregard this distance. We're not going to count that because remember, this is multiplication. If it's 1, then the distance computed for the feature will be included in the final score. So when this weight going to be 0, only two circumstances this weight will be 0. All the other cases weight will be 1. The weight will be 0 if I or j miss value for this feature. Okay, so because one observation missing value, there's no way for us to tell what's the distance. Therefore, we're going to disregard that. The weight becomes 0. The second situation where the weight will be 0 is if f is asymmetrical binary attribute and both I and j have a value of 0, negative. Remember, we disregard those, right? So we will use a weight of 0. Okay, so let's look at one example. How do we apply this complex looking formula? The idea is not complex. So we now back to our original example. Earlier, we only compute the dissimilarity when we only use asymmetrical binary attributes. And now we want to include our gender attributes into this computation. Okay. So the distance between Jack and Mary, in order to compute that, we have to compute for every attribute what is the similarity. And we need to decide for each attribute what is the weight that we're going to apply. Okay, so gender is, I'm sorry, again, I misspelled that. Gender is a nominal attribute. For nominal attribute, we will score the distance is 1 when the values are not the same. So our distance is 1. And our weight is 1 because it's not binary. It's not asymmetric attribute. Gender is not asymmetric binary attribute, and we have value for both attributes. Therefore, our weight should be 1. So this is this condition. Okay, for favor, we know favor is asymmetric. So if favor are yes, both are yes, then we will count that. So weight is 1, and the distance is 0 because they're exactly the same. Similarly, we do the same thing for cough. Test 1, test 2, test 3, and test 4. Okay, the weight will be 0 only when we both have negative values. So cough, negative. Test 2, both negative. Test 4, both negative. Those are the only places that we have 0 weight. And here the distance is simple, right? When they have exactly the same value, the distance is 0. When they don't have same value, test 3, when they don't have same value, the distance is 1. So once we computed all of that, we will use our weighted arithmetic mean formula to compute that. So our numerator is all the products between the distance and its weight, and the denominator is sum of all the weights. So we have 1, 2, 3, 4. Okay, so now we can compute the distance between Jack and Mary. Okay, so I'm going to stop this video right now and move on to a new video to discuss cosine similarity.